Welcome to the Bad Boy introduction tutorial. This will be very low effort, low production value, and I'm doing this voiceover afterwards, so there will be some distinct to what I do and what you see. So, first thing I'm doing is setting up some of the tools we're gonna need. I already have some tools pre-installed. You can check the description for what I have installed. I will be making some mistakes in command line stuff you see here. I have WSL installed for just easy scripting, Python, running makefiles. If you don't know how to, if that all sounds unfamiliar to you, uh, I recommend looking into that first because I won't be going into details of every single tool. I highly recommend joining our Discord server. The link will be in the description. Um, so one important tool that I download here is the BGB emulator. I generally keep a different copy of this emulator for each of my projects. The reason for this is that you can configure it differently. And for homebrew, you want to enable all exceptions. For general playing, you want to configure it slightly differently. So that's why I have a different copy here. Now, the game I'm going to look at is Ninja Gaiden Shadow for the Game Boy. I own this cartridge. I love the game. The music is amazing. Um, and I don't think anyone ever looked into this game. So I'm making a copy of the ROM here. I slightly rename it so it's easier to use in command line. It's not required, but just makes it a bit easier. And then the first thing we're going to do, we're not going to look at any disassembly yet. We're just going to take a very quick look at the general structure of this ROM. So any ROM is built out of banks. How many banks depends on the size of the ROM. And now I'm going to use the ROM to PNG tool, which is part of the BadBoy toolings, to just generate a beautiful picture of how this ROM will look as an image. Now, this image will, it's very insightful once you get a bit of a feeling for it. You can here see that I zoom into it, like on the right, you can see there's some graphics there. It looks like graphics. And there's on bank 5, there's some data. There's some more graphics in bank 2. And the first bank and the second bank, they look a lot like code. It's a bit, you get a feel for it. There's some empty space at the end of the banks. Bank 3 looks also like data. It's interesting. Just to get a general structure of the ROM, because it's looking at a ROM like this, it's a lot. Like, this is a relatively small ROM, but it's still a lot once you start to dig into all the data and all the code that's in there. So next step that I usually do is just running my emulator. I mess up the command line. As I said, I will do this a few times. I will mess this up. I run the command line. I run it with the ROM I want, and I run it with an output file. That output file will be an instrumentation file. This instrumentation file we will be feeding later into different tools. And here I just quickly, I use the speed up button, which is tab, to quickly speed through the intro and then exit the emulator with escape. This will generate this data file, this instrumentation data file, which I then feed into the ROM to PNG script. Why I do this, it's very simple. If we then look at the output, which we'll show in a bit, we can actually see the parts of the ROM that were used during displaying of that intro. So if we now see the PNG file, there's suddenly parts that are highlighted. There are highlighted star parts in yellow and highlighted parts in green orange. The orange green parts are code. The white parts are data. So my suspicion that there's probably the graphics in Bank 6 is it's probably a pretty good guess. There's probably intro graphics then at the beginning there. So that's useful to see. And now I'm gonna run it again. I'm gonna generate a second instrumentation file, but I'm going into the sound test. This game is special in that it has a hidden sound test mode. If you hold A and B, which is in this emulator A and S, while pressing start, you actually get the sound test. So I've run through all the different sounds, and my goal is just that the instrumentation file contains a bit of data on each piece of music and of a bunch of sound effects, and that will make it easy to identify where in this ROM is the sound code and data located. I have a suspicion where it is at this point already, but it's good to know it for sure. It's also good to know if it's just part of a bank or multiple banks or just the whole thing is really just to give you a starting point for later where to start looking, where you're interested in. If you would be interested in level data, you would load one level, generate an instrumentation file for that, load another level, generate an instrumentation file for that, and then later I can show you that you can actually take a difference. So this is what I will do after the sound test. I will take the instrumentation file from the sound test and remove everything that was hit by the intro instrumentation file. So you will only see the part that will be hit by the sound test. Now I first take this sound test. Well, you can already see, it touched a whole bunch of stuff in Bank 3, and well, that makes it very suspicious that Bank 3 is just all sound and music related code and data. It's usually located in its own bank. And now I'm gonna mess up with the how to run it here exactly. But now I'm gonna say, okay, I want the instrumentation of the sound test, and I want everything that's part of the intro removed. I'm actually gonna check the code because I'm an idiot and I should just have checked the -- help to see what the how it works. Here I'm like, oh, how did I program this? I forgot. Yeah, I could have cut this out of the video, but I'm a lazy bastard, so I didn't. So here now I know what to do. I say, oh, I want no instrumentation of the intro, or yeah, I want the instrumentation of the sound test and no instrumentation of the intro. And then all the parts that were part of the intro are no longer marked, and only the parts that were touched by the sound test are marked. So there's some stuff touched in Bank 5, which is interesting. I don't know why. There's some code in Bank 2, which is probably then the sound test code. So now I generate one more instrumentation file here, which is just playing of level 1. As I said, it's a fun game. It has amazing music. It has I think one of the best soundtracks of any Game Boy game. The stages are relatively short. I think I can beat it in 20-25 minutes, the whole game. Probably will take you some more if you do it for the first time, as the bosses have pretty specific patterns and the levels have think it's a fun game. It's well designed. I just do level 1 here as quick as I can. I will mess up a bit later where I forget what certain buttons do. Just using some of your skills requires a combination of key presses. Once again, I could have cut this out of the video, but now you get to see me play. Oh. If we think back at the ROM image that we saw before, we didn't see these graphics. So that's a bit of a shame. Some ROMs just contain uncompressed graphics. That makes it very easy to edit, very easy to use. This game clearly has some kind of compression going on. At this point in time, I don't know exactly what. Here's where I start to mess up the... Oh, I wanted to use that special ability and I messed up. Here you can see, oh, I still remember this secret. I haven't played this game in probably 15 years. And I still remember that you could go down there. No. Now at the boss, the boss music, I think the boss music is the weakest music in the whole game, which is a bit of a shame, especially because it's the same music for every single boss except for the last one. But yeah. So here I'm baiting the boss to actually fall straight down instead of doing a diagonal jump like that, because the diagonal one is way harder to dodge. But yeah, easy kill. And then we get this. I don't know how exactly they did this. That would be interesting to look at some point. The background, the enemy splitting is clearly some scanline effect. I guess the player is then done by sprites. So now I have also a level 1 data file. So I have 3 instrumentation files, which all contain different parts of the gameplay. I don't play through the whole game for instrumentation files. You can. It's a bit much. It's generally not needed to make the disassembler work, because that's what we're gonna do next. We're gonna take the ROM, our instrumentation files. Here I am messing a bit with. Oh, am I gonna type this on the command line? No, I'm not gonna type this on the command line. I'm actually already gonna set up a small shell script. You could also use a Windows batch file, but I have a particular reason why I use shell scripts. I start opening this in Visual Studio Code because now we're starting to actually look at text-related things. I hope this is all readable, else turn up the quality to the maximum in YouTube. So now I set up my scripts to run the disassembler. So the disassembler will generate a whole bunch of files with Gameboy assembly code in there. To be able to read this, you need to understand the Gameboy assembly instructions. A link will be in the description for the assembler used and also for the documentation of all these instructions. There have been awesome people documenting this really, really well. I also include a link to the pandocs or pandocs. I don't know how to pronounce it best. These contain all the documentation on how the hardware behaves, which is also, it's just a must read if you want to do anything with the Game Boy. It's if you're looking at this and you haven't read any of that yet, just pause this video, start reading that. Now, I finally set up my scripts here. I put in all the instrumentation files. I run it, and then it generates a whole bunch of bank files. It generates one file per bank. There's code in here, there's data in here. The instrumentation file causes it to, oh, I know what's data, I know what's code, but also it sees, oh, there's code here. This code could call out to other code. Even if it's conditional, it will put that into other, any code is traced like recursively. So a lot of code will be marked as code already, but it will miss parts. That will be fixing later. So now I generated an output, but it doesn't actually build. If I try to run make, I generated first in a temp directory just to see if everything works. And there is there's a bug in the disassembler here that I've run into. You will if you use this disassembler, you will definitely run into a bug like this. Not exactly this one, potentially another. Hit me on Discord. We'll see if the bug is easy to fix in the disassembler, or you just work around it. In this case, I'm going to work around it. It detected some like it sees here a label, and then at a certain point it decides, oh, some other space needs to have a reference to that label, and it did that in a wrong way. It generated a local label. It should have generated a non-local one here, but also this shouldn't have been a label. So here I'm going to say, oh, this should not have been a label. This should just have been a value. And that's what I say here. I add an annotation, and that's the add symbol. Add equal is value. It says, oh, this instruction should be a value. I also turn it into a value just to make sure that it builds now. After that it builds, it also checks if the output matches the original ROM in this make tab. So, and now once that's done, I can copy all that stuff from the temp directory. I copy it to my current working directory because that's where I want to work from. I don't want to work from the temporary directory. I just use that to make a build in a temporary directory, and then once that works, I want to copy it. Now, I'm making a small change here to the update script where I feed, and I first messed up because I do it wrong, where I feed the source code that I just edited back into the disassembler to generate a new disassembly. So this is important of how this specific disassembler works. You feed the disassembled source code into the disassembler to generate a new disassembly. That's a lot to take in, I know. But that here, with that add value is annotation, causes it to say, oh, I know now this needs to be a value and not a pointer. So it's no longer generating that wrong symbol, and then it works. So, and this is also why I create this script. So I create a script to first run the disassembler, check with make if it builds, and then if it builds, I copy the resulting disassembly back into my working directory. Now, I start the script with my set -EU, which is, I set it for the European Union. No, it's not the European Union, but it is basically that says if any command in the script fails, stop the script. So if this disassembler fails, don't run make. If make fails, don't run the copy. That is important part that I want. That's why I do the set EU. I don't want to run the copy if it doesn't build, because then I either messed up or something is wrong, and I want to check that by hand. Now, I do a small thing here. I change one label, but I don't even change where it's referenced from. It's referenced a few lines up. I'm not keeping it on screen very long, but it was referenced from there. I didn't change that. I only changed the label rerun the disassembler, and the disassembler updated the actual call to the label to name it like game entry. It's just a label I took. Um, we'll do more of these in the next video where I start actually looking at code like this, going to, oh, I know what this code does, and starting labeling things. Um, you can see there is a whole lot of code. This is just, it's 5,000 lines, and that's just the first bank. So there is just a lot of code always in these ROMs. And like I said, it's a small ROM. If we look at something like Link's Awakening, it's way, way bigger because it's, out of my head, it's like 8 times bigger. If we look at a ROM which I try to look at, but it's too big and too complicated, which is the Metal Gear Solid ROM. It's the biggest I've looked at. It's like over 200 banks. It's all filled with data. I think it's most of it's compressed. I went insane when trying to look at that. So start with a small ROM. I recommend starting with a Game Boy game, not a Game Boy Color game, because those are a bit easier. So here I take a look at um, Bank 3, where music data is located. And you can see that due to the instrumentation file, some stuff is already made into 16-bit words. Some stuff is already made into pointers. Like here, we see a bunch of stuff that's pointers. It's because the code, like running it, has seen this as pointers, or it's used as a pointer. The instrumentation file marks it as a pointer, like, oh wait, this specific data is used as a pointer. And then it turns into two pointers. Now, I add an annotation and add data annotation with format P. Say, oh, I think I have about 16 pointers here. And then run the disassembler again with the update script. And that causes it all to be pointers. However, when looking at the pointers, I see their code. So I'm changing it from a data annotation into a jump table annotation. This causes all pointers in there to be treated as pointers to code, and everything it points at will be turned into code. And any code that calls is turned into code as well. So that is a very powerful piece of this disassembler where just everything you turn into code traces to more code. Makes it really easy to get all the code sorted. It doesn't always work perfectly, but it works good enough. And that's also why I say you don't need an instrumentation file for the whole gameplay, because the rest of the code will generally trace out fine. So now I have a big table of data here. I don't know what it is. I just know it's a bunch of pointers. Instead of trying to count out exactly how many there are, I just rerun the disassembler multiple times, each time with increased values until I get like all the pointers. I'm very convinced this is music data. It looks like music data. I look in here and like, oh, this is probably music data because, yeah, it's a bit hard to understand how it's structured. If we scroll a bit down, we'll start to see this. And this is where we see a bunch of bytes, which are seen as bytes because that's what the dots say at the end of the comments. And there's occasionally a pointer in there. And that's what the P's are. And you also see that there's data pointers. This is very typical of music data. Also, at the end, you see a pointer back to almost the beginning. It's just the music looping. There's probably some references to other parts of music data or some other things in there. The music data is complicated, but it has a certain structure, even if it's different for every single game. Every game I've looked at so far for music data has a slightly different structure for music data. So I don't know what the E480 is. Could also be a pointer, because no, it could not be a pointer because that would pointing into VRAM. Um, so I don't know what it is. It's probably some initialization value or something. So there's another like interesting thing that I want to take a quick like peek at. Like I'm not going into any depth at the moment. That's more for other videos. But we see that there's a whole bunch of stuff there that looks like graphics, but it doesn't look like the graphics in game. Uh, so if we take our previous instrumentation file of level 0, of level 1, you can see a lot more is touched just to get to level 1. Almost all of Bank 0 code is touched. There's a whole bunch of data in Bank 4, Bank 6. I'm currently assuming Bank 5 is level data. It has this specific like structure to look at. I think this part that I'm zooming in now, I think that's player graphics. It has a few parts in there that look like player graphics, but it's not exactly player graphics. So I took a quick peek at how it looks in the bank and what the instrumentation said of it. And this is where things start to look odd, because it identified some parts as graphics. That's why there's the long numbers there. But some parts are identified as 2 bits per pixel data, and some of it is 1 bit per pixel data. And that has to do with how all the instrumentation works. But that leads me to think, oh, there is a certain type of compression going on. I think I understand sort of the type of compression, like the general idea behind the compression, where you repeat certain bytes, and that causes them the instrumentation file to see it as, oh, that's just 1 bit per pixel data. But I don't know the details right now. So another thing I want to quickly show is the BGB emulator. It's the one I use even if I'm on Linux. You can do all of this on Linux, just to be clear. I use this emulator. I run it in Wine. It works perfectly in Wine. It's my favorite emulator. I know all the shortcut keys. I occasionally will use shortcut keys. I'll try to mention them if I use them. Like here I press escape. Escape gets you into the debugger. And if you're in the debugger and press F5, you get the video memory viewer, which is an amazing tool to use just to see how graphics are loaded into video memory, which graphics are loaded, how sprites are used. It's useful for debugging. It's useful for reverse engineering. You can look at the code. You can also see in the code that due to I'm loading a build I made from the disassembly, the code view on the top has labels on there that are in the assembly. So here I quickly look if I see the OEM shadow memory, but I don't directly spot it. It's usually at the first address in work memory, and it is not for this game. So I don't dive more into it because I was like, oh, if it's there, it's good, but it's clearly not there. There's some other data there because you see some memory values changing. So But I want to do something simple, so we can see we have 2 lives, and I want to know what memory location our lives are located. Which is very easy. We're just going to use a cheat searcher, because the cheat searcher, well, it's very useful for cheats. It's also very useful to find where specific memory values are located if you know what the value is. So I first search for 2 because, well, I have 2 lives. And then I just reduce that to 1. Now, in this case, this works flawlessly. I just get 1 memory value. I go there in the debugger, go to that value. I change it to 4 just to verify, oh, is this the actual amount of lives? You don't see it updated on the screen immediately. Also not if you press pause or anything, because the screen is like, this is happens a lot in Gameboy games where the screen is only updated when it's needed. So, but now we can see, oh, it's turned into 3. So this value is clearly our number of lives remaining. So we go into that. We go to that memory location in the disassembly. Change the label to lives remaining, and then we can just run our update, which will change any reference to this. I still have, like, here you can see, oh, life remaining starts at 2. This is probably where we start a new game. Apparently something is also initialized to 6, which is probably your amount of health. Here 70 is added, which is weird. Why would it add 70, like 17 hex, to the life remaining? You initially might think, oh, maybe we relabeled the wrong thing. But no, this is just, if you go into the VRAM viewer that we had before, I'm keeping the debugger open to keep it paused, and go into that specific tile, you can see the tile number. It's below the zoomed in version of the tile. I will point my cursor at it. It's 73. So this is just the place where it draws this specific tile to the screen. You can also see the map address is referenced from the code there. So our initial guess of this being life remaining, it has to be pretty much accurate. So that's it for today. I'll see you on the next one. I'm not going to tell you to like and subscribe, because fuck that.